Guys, this video we will talk about cutting tabs. The last video
Welcome
spoke
back.
about drill, the types and ways to machine it. We also seen that the material that the cutting tool itself will be made has an important effect on the machining parameters such as the cutting speed and the feet at which the blank will be cut will depend on what type of material are we using to make the tool. Most commonly used materials are high-speed steel with cobalt, and carbide. We see that high-speed steel is the most commonly used drill bits in a simple applications as carpentry and a lot of simple day-to-day use. Most of the carbide tools are used on a expensive high-speed CNC machines. Depending on the application, we also seen that the cutting tool manufacturers will opt for high-end coatings. Some of the basic coatings such as the bright finish coating, black oxide coating, tin coating will be used for not much highly demanding applications. Highly demanding applications where you need to machine Inconel, high strength steel, high strength alloys, you need to have a phenomenal coating capabilities of the cutting tool. So the cutting tool needs to make sure that it has enough fracture resistance, good surface hardness, excellent tool life, and at the same time provide fantastic lubricity in the cut. Now let's come back to the tabs. As you can see on the layout I have on the screen, I have three types of tabs pulled in. And these are the three common types of tabs out there that are available for selection based on the workpiece geometry, the application that need to be employed to get an extreme performance at the end. Okay, let's see the type 1. So the type 1, this tab, it's called a straight flute tab. As you can see, the flutes, they don't really tell the chips which way to go, either to come out or go down into the hole. So this, you can see these are straight flutes with a chamfer of just 1.5 pitch. Now let's look at the second type of tab. So the second tab, as you can see, it's called a spiral flute, spiral point tab. With the point geometry, you can tell based on the helix angle, is a small spiral to it, as opposed to spiral flute tab, as you can see the helix of around 30-degree angle. So the way the helix are done on the spiral flute tab, the chip will be pulled up and away from the hole. So if this is the hole right here, as the tool goes and feeds in, the chips will be pulled out. Whenever in the tapping application, it's highly critical that we have to synchronize the feed movement of whatever the axis is the tool mounted on. So normally it will be in the Z axis, the tool will be mounted in the Z axis, the holder. So it will be feeding in on the negative Z into the workpiece. It depends on the type of machine that we use it on. On a lathe, you'll be feeding, you'll be either using a live holder or a stationary holder, also called as a stick-out holder. On a mill, it will be in a floating, either a floating holder, or if it's in a rigid tapping, will be on a machine where the feed on the z-axis will be synced with the rotation of the spindle. Let's go back and do some cut section. Let's go back here, go back to insert, datum plane. Let's select 0. Okay, let's go to select, go from body, select and curve, let's select the object type, all three. Let's go back and say assembly. Okay, select OK. Out. Okay, now we got the curves for the taps. Okay, we have seen that there are three types of taps. One is a straight tap, spiral point, and spiral float. These are straight floats, spiral point, and spiral float. And again, the type of chamfer or lead-in that's on the tip of the tap itself has three types. One, the bottoming tap. Bottoming tap will have anywhere from a 1.5 to 2 pitch. Spiral float and spiral point, mostly spiral float will be mostly bottoming tap, 1.5 to 2 chamfer, 2 pitch chamfer. Spiral point and taper plug will have anywhere from 6 to 4 pitches of lead-in on the tip. It will be a nice lead-in. Okay, let's go back and edit, hide bodies. So what's the pitch? Pitch is the distance from one thread to the next. It depends on if you select the crest or the peak, from one peak to the next. So here, let's go back and check the distance. Get this vector, go back and select. Okay, 2. So now this is the pitch of this tap, which is 1.25 millimeter. Okay, now go back here, hide. So in hide, solid bodies. Okay, now let's go back and do a go back and hide these curves. Oh, it's all hidden now. Let's go and select a block where we'll make a threads. We'll make a threads with a fine pitch, the coarse pitch, or a medium pitch. And I will be able to explain to you why it's critical that during a rigid tapping we need to have a holder that will locate the flat the shank of the tap in the collar, so it's squarely and actually located, so that gives a back support and held in, clamped in for rigid tapping, so that during the feed of the axis the spindle rotation will be synced with the feed rate of the tap itself. So like this. Okay. Extrude, sketch. Okay. Let's go back here. Body. So let's go back and insert. Now let's go into manufacturing module of the NX to demonstrate the things that we talked about. Let's create a toolpath to make 3 different types of tapping operations. Let's make one coarse pitch thread, one fine pitch thread, and one medium pitch thread. Let's use this face to create a sketch where we can able to use the tapping application. Okay, insert, sketch, select this face. So I'm going to draw a sketch, circle, cancel this. Let's create a 1 metric thread, 8mm thread. So 8mm into 1.25. 1.25 is the pitch. M10 into 1.25 and M12 into 1.75. The second number is always the pitch. As we had did in a cross section cut, we select the distance from one pitch to the next. That's the distance. That's the pitch distance. Now, the thread height is the difference between the major diameter or the minor diameter. So what's the height of the thread is the difference between those two radially. Okay, let's go back and do this. Let's go back and create the diameter what we need. Okay, so it's a metric M8 thread times 1.25 pitch. So M8 is the major diameter of the thread. Subtract that by the pitch 1.25, you will get 6.75 is the nominal minor diameter that we need to hold. So that's the drill bit we need to select. Second, let's do the 10mm thread. That's M10 into 1.25. Again, now M10 is the major diameter and 1.25 is the pitch. Subtract 10mm minus 1.25, you get 8.75mm. Okay, now we can come out of the sketch. Let's go finish sketch. Go back and extrude this. So change the direction of the cut you want to make. You need to subtract it from the block. The distance is going to be okay. Check it's doing right. Looks right to me. Let's go back and put a chamfer. So for the chamfer, at least give the size of what the pitch, so that you will have a nice lead in for the tap. Let's go back and give it 1.3. Okay, looks good. I'll go back and edit. So on hide all the sketches and curves. Okay, so get your clean view. I'll go back, insert, design, thread, go back detailed, select the cylindrical face. We know this one we need 8mm. Start face is going to be here. Reverse 6.75 is the minor. length. Obviously the length 20 millimeter is the distance where we need to drill. Now for the thread depth itself, we need to back up the depth at least 3 pitches above the drill depth from the flat of the drill depth. Reason being is as we start tapping it, it's a cut tap, so we need to give some distance for the chip to have some space. We don't want to pack the chips, the next thing you know, we're going to snap the tap. Again, snapping the tap failure depends on a lot of factors. One being not enough coolant in the cutting zone, not enough lubricity, too high of a surface footage. Just remember guys, the surface footage comes from the material they were trying to cut, the tap material, the coating on the tap itself, as we talked about, tin coating for high performance coating such as titanium aluminum nitride. If it's a titanium aluminum nitride, since it's an aluminum, you cannot use that coating on aluminum blocks, aluminum workpiece, but you can use a titanium carbonitride coating taps. All the manufacturer, the tap manufacturer, if you look at the illustration, all the taps will have a color code. Each color represents what type of workpiece it will be used on, starting from low carbon steel, medium carbon steel, high carbon steel, high strength steel, heat resistant steels, high strength alloys, you name it, different titanium, stainless steel, different type of stainless, 300 series, 400 series. Like I told you, the tap, whenever there's a failure more in tapping, you need to analyze the risk, try to figure out the root cause, go one by one. Select the right side cutting surface footage. It comes from the book, manufacturer book. Again, each tap will be color coded based on the workpiece that will be using it to cut the tap on. Okay, so now this is the distance we gave during extrude for the drill. So you need to back this up. The pitch is 1.25. So take 20 millimeter minus 2 pitch. That will lead up to 17.5. Looks good. Select OK. Now you get a nice thread here. So you can see, since it's a through hole, it's not a through hole. I'm sorry guys. Okay, if it's a through hole, you know what tap to use? Best tap will be used on spiral point tap, or you can use a straight flute tap too. Being a spiral point tap, you know the way the flutes are ground, the helix angle are put in, you will try to push the chips during the cut inside the workpiece. So if it's a through hole, guess what? So you have a room for chips to get out of the hole, so that nothing will have a devastating effect on the tap itself. If it's a blind hole, it will be best to use the tap right here. You can see it on the screen. It's a spiral flute tap. So you can the way the flutes are ground, you'll help in evacuating the chips, pulling all the chips from the cutting zone away from the workpiece through these flutes and away through axially up. Okay. All right. So if it's aluminum, mostly if it's for aluminum, if it's aluminum block, if it's some soft material, most of the people what they try to use is, instead of cut taps, all 3 taps that I discussed, the taps in the picture that we saw, spiral flute, spiral point, tapper plug taps. Cutting taps are used for mostly steel. If it's aluminum, most of the people use form taps. Form taps, the difference between the cut tap and form tap is based on the core diameter or the minor diameter. So for the cut taps, if it's you take the major diameter, subtract the major diameter by the pitch, you will get the drill size used for the core diameter. So that will have enough clearance for the tap to go and make the threads. If it's a roll form tap, again obviously you can use a higher you need to use a bigger size core drill. So if it's same thing for 8 millimeter, if it's an M8 into 1.25 pitch, you'll be using at least 7 millimeter drill size as to make your core hole. Again, for depending on the applications, if they want really good threads, the thread percentage will be specified on the drawings. The thread percentage starts from 60% thread or 75% thread. Obviously, the higher the percentage of threads, that means you need to use that. They'll change the core size, the drill size of the before the tapping application you'll be using. Let's go back and do that. 10 millimeter. So this is 10 millimeter. Insert. Change the axis. 10 millimeter 8.25. Do the same thing. 7.5. Okay. So now let's go back into the manufacturing side of the NX. Let's go select manufacturing. For all the whole applications, the number one criteria is you need to check the length by diameter ratio of the hole that you're trying to do. So as long as the length by diameter ratio is less than 3, that calls for a really fantastic, robust manufacturing part. Reason being is now you can use the stubby drill, you can use from the spindle to the cutting zone itself, the distance of the overhang will be much less. So everything will be a highly rigid process. Now we have a cam, select cam, this is fine. Now let's go back and select the MCS. So that means you need to create a datum thesis that will represent your machine coordinate system. It's going to be a simple 3-axis mill. We don't have to think about too much on selecting multiple MCS and whatnot. Go back and select the MCS. Okay, right here, right in the middle. Looks good. Or if you're going to use the edge finder, you can pick one of those edges. Or if you're going to select both the center distance between the two faces, you can leave it as it is. Okay. Now for the workpiece, let's go back and specify the part. Okay. For the block, select from bounding block. That looks fine. It's fine. Let's go back and select the tools. Okay. Now we need to create a spot drill. Let's do the spot drill. So if you are going to use like we talked about the point angle, it's going to be a self-centering drill. You don't need to spot it. So in our case, let's use a self-centering drill with an excellent web design, helix design, double margin drill. For the first threaded hole, it's an M8 into 1.25. So the drill size we need to pick is 6.75. So 6.75. Okay. I think I need to select the drill. I'm in the wrong pop-up screen here. Let's go back and select the drill. Ball mill. Let's start selecting the tooling that we need to create the tool path. So we need that, we said that we need a drill. The drill need to be to the size of what we did the math on. We know that we do have two different threads, M8 into 1.25, M10 into 1.25. So based on the math that we said, we're going to subtract the pitch from the major. It will give us the drill size that we need. There's a drill chart. You can use that too. That'll be easier. Or you can use this. When you switch between the standard threads and between the metric threads, sometimes it will be a little bit of confusion because the standard threads will be given in threads per inch. So I need to say half 13 threads. You need to take so that's 13 threads per inch. So 1 by 13 that gives you 60,000 pitch, or a quarter 20 that will give you 20 threads per inch. So 1 by 20 that's 50,000. So if you want to use a drill chart, or you can use a simple formula like what we talked about. So now we know that we need to use a drill with a point angle of 138. So that will tell us, since it being a flat face, we don't need to use a spot drill or a center drill to make sure that every time we go and call the drill bits, that's based on the length by diameter ratio. With the ratio is a little longer, you don't have the problem of drill having a run out on the drill or the drill walking on us, because it's a flat face and we have the length by diameter ratio with excellent aspect. That's good for manufacturing, right? So we need to go select the drill bit. Drilling tool, you know that it's going to be a 6.75 millimeter. Okay, point angle 138. Okay, no corner radius. Length, sounds good, sounds good. Tool number 1, register 1. So since being a drill, you will be only using a Z-axis. What are the axes the drill is mounted on? You'll be using only that axis, plus or minus, to either go deeper or shallow. Go back and select the holder. Let's give it a 6.75, so it's going to be a 15 millimeter. Collet, probably the collet you need to use a precision collets. You can ear collet, rigor fix collet. Different companies, a lot of companies make them. So length, let's give it 50 millimeters, upper diameter. So it's going to be a taper. So it's going to be like 25. Okay. So let's select the next, since being a cat 40. Let's give it a 50 millimeter, 25 millimeter, 50 millimeter. Okay. So it's going to be, all right. Looks good. Okay. So we need to select a second drill for this second tap hole. It's going to be a M10 into 1.25. So it will be 8.75. Again, it's going to be a point angle of 138, self-centric drill on a flat face. Okay, looks good, good. Obviously, it's a drill, it's 2 flute. It's going to be end mill, depending on the type of end mill. For finishing, you need a higher number of flutes. Odd number of flutes give you very good spacing. That give you keep all the harmonics, depending on what you like. Since it's being a drill bit, it's going to be only 2 flutes. Tool number 2, register 2, holder, do the same thing. Okay. Now we need to select the 2 different taps. We need to select the tab. This is going to be a 10 millimeter into 1.25. 8 millimeter, I'm sorry. So I think we need to give too much of spacing. No empty space. Okay. So then diameter is going to be 8. Neck diameter, let's give it 6.2. You need to have a room for chips to go out. So it's always used a smaller neck, tip, length. Okay, taper, always use light taper on the tab. The pitch right here is 1.25 millimeter. So give it a 3 on 3. Okay. Select that. Next step is going to be, this is going to be a 10 millimeter times 1.25 pitch. Okay, it's going to be 10 4 and 4. Okay, now let's go back and select our MCS. Okay, this is good. Workpiece. Okay, bounding block. Okay, select operation. All right, now it's going to be selecting the drilling tool. Okay, MCS method. Go back and select the holes. Select. Okay, this one. Then select this. Okay, top face. Give it a 3. Okay. Right. Okay, tool, select the drilling tool, change settings, standard row. So CAN cycles, most of people who use the CNC will know about the CAN cycle, G81 cycle, G83 cycle. If the machine has a excellent through coolant capacity with a good pressure, coolant coming out, and you have a through coolant drill, you can, even if the 6 or 7 length by diameter ratio, you can use a single shot G81 cycle. The reason using a G83 picking cycle is whenever the drill goes back and up, retract from the hole and trying to get back in, there's going to be a fracture resistance trying to compromise the fracturation of the drill bit itself, because it will be bad for tool life. So as long as you have a good coolant, just do G81 cycle. Again, it's you need to be conscious of the length by diameter ratio that you're doing. So let's go a G81 cycle here. Standard drill, main clearance 2 millimeter. Usually for a high speed production, people go 1 millimeter. Okay, now let's go back and select your surface speed. It comes from the book, manufacturer book. They will specify it based on the workpiece you're doing. They'll tell you what's the surface footage. Let's get 50 here. Let's go 50 micron. Mostly I program in inches, so it's kind of little. Okay. Okay, let's check. Okay, fantastic, looking good. Now let's copy this, copy, paste inside, go back in, specify a different hole. Okay, omit existing point, say yes, select this, okay, and that, and then select the tool to be 8.75 drill bit, so this one. Okay, so the first one is going to be a 6.75 millimeter drill for M8 threads. Second is for the M10 thread, 8.75 millimeter drill. Looking good. Let's go back and do the tapping cycle. Go back and select the tap here. Okay, you need to tap 8 millimeter. Yes. Specify holes. Select point. Always be looking at the notifications you're getting. Anything pop up, look for that. They'll give you a lot of details what you need to look for. They'll never, when you kind of ignore those stuff, that's when the trouble finds you. Select OK. Okay. Most of the machines nowadays, CNC machine, they have G84 rigid tapping cycle. They select the R plane, retracting plane, bottom face. Okay, taps are good, good. Whenever rigid tapping, we need to sync the feed rate of the tool mounted axis to the rotation of the spindle. Let's give it a, we don't want to tap the distance all the way to the bottom of the hole. We need to back out at least 1 thread pitch. 2 thread pitch is good, so let's go and do 3 millimeter right here. So that puts up the bow. Go back to shift, put in this, go back here, shift, another program. We need to make sure that we are selecting the avoidance plane, advanced retract. Okay, I will go back and post it, and we'll use the Vericut for simulation in the next video. Thank you for watching. Bye.